What kind of integer n makes this polynomial a perfect square? First of all, I want to complete the square. So I want to write bracket n to the power of 2 plus an plus b square. And then that equals according to our polynomial square formula, we have n to the power of 4th plus a square n square plus b square plus twice of this times that, a n cube plus twice of this times that, twice of b n square plus twice of this times that, 2abn. Okay, then I want to compare this with that. So, of course, I have to combine some terms, right? N to the power of 4th plus 2a n cube plus a square plus 2b n square plus 2ab n plus b square. Right, then I want to compare, right? 6 equal to 2a. So that means a equals 3 should be good. Then a squared becomes 9. 9 plus 2b equals 11. So that means b has to be equal to 1. So this is good. So a times b equals 3. 3 times 2 is equal to 6. 6n. 6n is different from 3n, but that means we only have to minus 3n to make up that polynomial. B squared equal to 1. There I have 31. That means I just have to add 30 at the end. So in fact, my polynomial, original polynomial, let's denote it as k. Right, so that means my perfect square can be now written as n squared plus 3n plus 1, right? Like I said, a equals 3, b equals 1. Right, so that means my original polynomial, denoted as k. K now can be written as this, first of all, this perfect square. N squared plus 3n plus 1. Quantity square. Like I said, in the end, I have 3n plus 1. So 6n plus 1. There I have 3n plus 31. So that means from here, I should only just minus 3n and plus 1, plus 30. So that means this is exactly the same as my original polynomial. So how can I, first of all, my feeling is that, how can this be a perfect square? First of all, maybe this equal to 0. Then we have a perfect square. That's fine, right? That's obvious. When n equals 10, this becomes 0. So this is fine. So how about when this term is positive or this term is negative? What will happen? My intuition is that, first of all, this term is only a polynomial of degree of just 1. But inside here, we have a polynomial of degree of 2. Then we have to square it, which will become way larger than this term as n gets very, very large enough. So, in other words, could this whole term be a perfect square that's larger than this perfect square or smaller than this perfect square? In other words, if I have 6 square, right? If it doesn't equal to 6 square, then could it be equal to 5 square? Could it be equal to 7 square? Right, because there is no perfect square in between those two numbers or in between those two numbers, right? Could it be that? Could it be this? Could it be 4 square? Could it be 8 square? And so on and so forth. So here, because the next perfect square after this one is the inside, the plus 1 quantity square, right? So 6 plus 1 equals 7, 7 square, something like that. But then I have to square everything, right? But notice inside is a polynomial of degree of 2. So it's going to turn out to be, way larger than this one as n gets large enough. So my feeling is that may not turn out to be the next perfect square as n gets very large. But if n is small enough, maybe it's still possible. Likewise, could it be the previous perfect square? Could be, if n is small enough. Right? It just could be, but if n is too large, then it may not necessarily be the case. But let's check it out. So that means let's check the previous consecutive perfect square case first. So in other words, when this term is negative, so when n is larger than 10, what will happen? So if n is larger than 10, so that means this term is negative. That means this whole term will be strictly less than this term, right? So that means in order for it to still be a perfect square, this whole thing has to be strictly less than this perfect square, right? So I have to, in the case of when n is strictly larger than 10, I have to make sure that this k is strictly less than this perfect square, right? So n squared plus 3n plus 1, quantity square. In other words, k is, so for k to still be a perfect square, first of all, it's strictly less than this. Then that means is less than or equal to the previous perfect square. So that means n squared plus 3n plus 1 minus 1. Quantity square, right? Just like here, for k to still be a perfect square, if it's strictly less than 6 square, that means it is less than or equal to 5 square. Could be 4 square, could be 3 square, but it should be less than or equal to 5 square. So that means it should be less than or equal to the previous perfect square number, right? That's minus 1 here. So here I can just say that what's k here? K is equal to this is less than or equal to that, right? So that means n squared plus 3n plus 1. Quantity square minus 3n plus 30 is less than or equal to n squared plus 3n quantity square. Right, we can treat n squared plus 3n as a whole thing, right? N squared plus 3n. So square everything, we have this quantity square and this quantity square. They can just cancel out. And I have twice of this times 1. Right, so I have twice of n squared plus 6n plus 1 squared plus 1. Right, minus 3n plus 30. Less than or equal to 0, because this one is cancelled out with the previous perfect square. Now I have to, just work out the inequality, right? So 2n squared plus 3n plus 31 is less than or equal to 0. Is it possible for k to be still a perfect square? Well, just check the determinant or the discriminant. b squared minus 4ac, right? 9 minus 8 times, so whatever. So it is already strictly less than 0. So that means this this square, so this function should be strictly larger than 0. It's graph, right? So that means it cannot be less than or equal to 0. Right? That's the graph of a parabola, right? So no, not possible. How about when n is strictly less than 10? Is it possible? We've just established it's impossible for n to be strictly larger than 10 and still to make this polynomial a perfect square number. Not possible, because we've proven that in the end, this whole thing, if still being a perfect square number, it cannot be less than or equal to the previous perfect square number, which is n squared plus 3n quantity square. So it's just like the number is stuck in between 5 square and 6 square. Cannot be less than or equal to 5 square at all, right? Strictly stuck in between those two numbers, right? So strictly stuck in between perfect square of this perfect square and the previous perfect, that is n squared plus 3 and quantity square. That's why. Now, the last case, when n is strictly less than 10, is it possible? So which means when n is less than 10, that means this term is strictly larger than 0. So that means in order for k to still be a perfect square number, and at the same time strictly larger than some square number, in other words, just like here, it has to be strictly larger than 6 square, meaning it has to be larger than or equal to 7 square. In other words, this has to be larger than or equal to the next perfect square after this perfect square, that is n squared plus 3 and plus 2 quantity square, right? So, so for k to still be a perfect square, first of all, it is strictly larger than this. So that means it's larger than or equal to inside plus 2, right? So n squared plus 3n plus 2. That's the next square number right after this one, right? So that means k is equal to that. So that means n squared plus 3n plus 1. Quantity squared minus 3n plus 30 is larger than or equal to n squared plus 3n plus 1 plus 1. Quantity square. Treat n squared plus 3n plus 1 as a whole quantity, right? Then we can perfect square. So that means in the end, this will cancel out with this square. We have to twice of this times 1 and plus 1. So that means this is gone. We're only left with minus 3n plus 30 is larger than or equal to twice of this thing. That is 2n squared plus 6n plus 2 plus 1. Right, so we can just rearrange everything, and so that means we move this term over here. So that means 2n squared plus 9n plus 3 minus, so minus 27 is less than or equal to 0. Is it possible? All right. So we can just quickly work out the two roots here, right? So n1 and n2, right? So n is equal to 81 minus plus 8 times 27, 8 times 27. 297. Correct. 297 divided by 9 is 33. Yeah. So this square root can be written as square root 9 times 33. So extract 9 out. Becomes 3. Right? So n equals 4 minus 9 plus minus 3 square root of 33. Then we could quickly just work out the, so in the end, I'll just skip the steps. And so in the end, we will find out its two roots are strictly, one of the root is strictly larger than minus 7, somewhere here, right? And the other root is strictly less than 3. Right, so for this parabola polynomial to be less than or equal to 0, first of all, we cannot, n cannot be equal to minus 7 or minus 3, right? Because its two roots are somewhere here and there, so it's so open upwards. So something like that cannot be less than, cannot be strict minus 7 or plus 3. Otherwise, it will be greater than 0. Not allowed. So in other words, n is restricted in between minus 7 and 3. Right. So in other words, the only possible possibilities are n equal minus 7, or minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, and 2. Right. So this is not saying that. This is not saying that as long as n equals to following numbers, this will definitely be perfect square. Not saying that, but this is the minimum requirement, a necessary condition, right? But we still have to test out every number. So I just skip the steps and just reach to the final outcome straight away. So after we test out every single one of those numbers, it turns out to be that none of these numbers makes this a perfect square. So no. So the only possibility is that when n equals to 10, that's the only number that makes this polynomial a perfect square.